Okay, so today we'll talk about electromagnetic waves. Okay, so before I do that, let me give you a little history. So you guys know what the speed of light is?
300,000 kilometers per second.
So 3 times 10 to the 8 meters per second. 3 times 10 to the 5 kilometers per second. Yeah. Uh, the first attempt to measure the speed of light was around 1600 or so. And it took us about 200 years to measure the speed of light. Yeah. So we weren't able to measure the speed of light for essentially 200 years. Okay. And so we had measured the speed of light, but we didn't know the nature of light. Okay. So Mr. Maxwell was the first one who realized that light is are electromagnetic waves. And this happened around 1880 or something like that. Okay. Again, my dates might not be accurate, but okay. And this chapter, we'll learn how he discovered that. Okay. So again, we will talk about electromagnetic waves, and like the name suggests, these waves are composed of both electric and magnetic fields. Okay. Now, before we get into this, let me show you something that you have learned in Physics 1. Okay. I'll remind you of the wave equation, but before I do that, okay, so to create a wave in a medium, you have to pump energy. So here's this oscillator that's pumping energy into the medium, and this wave is carrying away the energy. Soon as I stop this, oops. Oh, well. As soon as I stop pumping energy into the medium, the wave stops. Okay. Well, I mean, all right, so the wave that has gone will keep propagating. Okay, so you have to have something to pump energy into the medium, and the wave carries the energy away. Okay, now if you look at this, okay, so let me pause it again. Okay, what we're going to do is, so there is the undisturbed, the dashed line is the undisturbed position of the medium, and then you can see that, so this is the one-dimensional wave, and the y coordinate of the string changes with x, right? So the y is here is a function of x, the disturbance of the string. And what else is it a function of? Time. Okay. So y, the position of the string, is a function of x and t. And it turns out that, so remember, whenever we want to study a system like this, what do? Very good. All right. So we want to come up with a mathematical model for this system. Okay. The motion of this string obeys this differential equation, partial differential equation. Xt. Okay. So it obeys this partial differential equation, and this is the wave equation. Okay. So what it's doing is, it's relating. See, oh, and what does partial derivative mean?
Take the derivative of one variable and treat the other as a constant.
That's right. Okay, so this is, okay, so let's go back to that simulation. Okay, what that equation is doing is, it's relating the change of y with respect to x, how it's changing with respect to x, to the change at a given location with respect to time. The two are related. Okay, and that's the wave equation. And you have all kinds of, so the water waves, you drop a rock on a lake, you have electromagnetic waves, and all those guys obey that differential equation. So now we'll show you that in an electromagnetic wave, the electric and magnetic fields obey that equation. Okay? And that describes a traveling wave. Okay? So that's the wave equation, and let me actually write it neatly. Okay. Del square y x. Okay. And I'll point out one thing. So dimensionally, this is a distance, and it's a second derivative, so you have distance square here in the bottom. Distance, and then velocity times time is distance, so distance squared. Okay, so that's where the velocity comes, and that's the speed of the wave. Okay. All right, now we'll talk about electromagnetic waves. So here's a simple example of an electromagnetic wave. Okay, so here's a wave, and here's this laser beam. Okay. And in this laser beam, you can measure